usually we have the crystal and the isotopic phase, and between we have the famous nematic phase, in which we have some kind of order, like in the solids, but we also have some kind of disorder in the sense that the center of mass of the molecules can be randomly ubicated in the volume. But in terms of liquid crystals, we can also have other kinds of strange phases. For example, we have the symmetric phase, in which we have more positional order, because the molecules are ordered in layers, but each of these layers have a positional disorder and only have orientational order. Or we have the chiral nematics or cholesteric liquid crystals, in which the molecules are also ordered in layers, but each of these layers is tilted in a different angle in order that they make some kind of helical structures. Thermodynamically, in particular, in this research, I'm gonna focus in the nematic phase, which is characterized by being presented in materials which molecules are very elongated, usually formed by two or more aromatic rings and constituting groups that unite these rings. The properties of the material, the liquid crystalline material, for example, the response of changes on temperature or external fields, are a direct consequence of the constituting groups that are in the molecule, or the molecules in the case that we have a mixture of liquid crystals. Thermodynamic liquid crystals are widely used in industry. For example, we have the classic application in liquid crystal displays, but we also have thermal sensors in order to see if we achieve some kind of temperature. And we also have other sophisticated applications, for example, the made of lenses, using liquid crystals instead of glass. So how can we modulate mathematically the patterns and defects that we can encounter in liquid crystalline materials? If we are in constant temperature, the dynamic of the liquid crystalline material can be modulated using this director vector n. The director vector n is by definition, the average orientation of the molecules in different points of the material. And the evolution of this director vector is dictated by this dynamic equation, which is associated with the free energy of the material. Now, the free energy of the material can have two main origins. It can be from elasticity stresses. The molecules will tend to align parallel to each other. So any deformation from this parallel orientation will generate an elastic stress that we can modulate as a change of energy in the material. We have three main different ways of deform this material. So we have three terms in this energy for the elastic stresses. And we can also have an energy that comes from the interaction with external fields as a consequence of the charge distribution of the electrons in the molecules of the material. So in order to observe defects in this kind of materials, usually what we use is a nematic liquid crystal cell. A nematic liquid crystal cell is made from two glass plates parallel to each other in this case. And we put liquid crystal inside these two glass plates. And the idea is that if we use some kind of anchoring in these glass plates, for example, if we use homotropic anchoring to make that the molecules are aligned perpendicular to the glass plates, the elastic stresses we're going to generate an orientation roughly perpendicular to the nematic liquid crystal plane. So, in this case, if we apply an external, for example, electric field, and if the dielectric anisotropy of the material is negative, we'll have that the molecules will want to align perpendicular to this external electric field. But we also have the elastic stress coming from the material, so we have this competition between these two steps. The idea is that if we apply an intense and not too intense electric field, the tilt of the molecules from this theta direction, that is the direction perpendicular to the plane, will be roughly small. And also we can modulate the projection of this tilt in the XY plane, that is the plane that is parallel to the nematic liquid crystal cell. If we use this tilt as a very small tilt, we can modulate the vector director using just two components, U and V. And in particular, if we impose the boundary conditions imposed by the homotropic anchoring, we will have that the ansatz that we can use for these two components of the director vector will be the first mode associated to the distance that they can cover in this direction, in the direction perpendicular to the plane. If we use this ansatz in the previous dynamic evolution, we will have that for a first order, the evolution of these two components of the director vector will be dictated by this equation. This is very interesting because this equation tells us that for intense enough electric or magnetic field, the external fields will the external field interaction will be greater than the elastic interaction, so the molecules will tend to fall in some kind of angle, as I explain later. So in particular, if we use no magnetic field and we use an electric field that is only perpendicular to the plate, we will have that for a intense enough electric field, that here I am modulating using a voltage difference between the two plates, we will have a transition from this vertical direction to a tilted direction in every point of the cell. This is called the Faraday transition. And in particular, this transition is a degenerated pitchfork bifurcation. It's a pitchfork bifurcation because we have the vertical direction, and then for a critical value, we will have the tilted direction for the molecules inside the cell. And it's degenerated because the molecules can fall in any azimuthal angle in this XY plane that is parallel to the nematic fluid crystal cell. So this is what we need to discuss until now for nematic fluid crystals. Now I want to discuss some characteristic of topological defects. In physics, a defect is a singularity which breaks some kind of symmetry in a system. The most classic case is the dislocations in crystal ordered materials. In this case, or in some cases, the defects in a system are topologically protected, which means that they cannot disappear by continuous variation in the system. So, for example, we have this kind of defects in the hair of some animals, like humans, but we also have this kind of defects in the hair of some fruits, like the coconut. We also have some kind of defects in the digital prints of our fingers. And we can have this kind of topological protected defects in different contexts, as for example, in the wire of old telephones, that you maybe can remember this kind of defects that can only be destroyed by the boundaries, or if we collide with another opposite topological defect. So more precisely, in 2D fields, we can modulate this field using a complex form. In particular, in the cases where the magnitude of this complex parameter is 0, we will have that the phase of the parameter will be undefined, and we will call it a phase singularity. The idea is that the way in which the ordered parameter is oriented around the phase singularity can be modulated, is completely characterized by this parameter Q. So the value of Q, that from now on I'm gonna call topological charge, indicates the type of topological defect we can find in a system described by this 2D ordered parameter. In the image, for example, you can see how different values of Q has, as a consequence, different ways in which the ordered parameter is oriented around this topological defect, this phase singularity. Okay, well, this topological charge can also be defined using this closed integral, which accounts for the difference in orientation of this ordered parameter around a loop, around a closed loop. And the idea is that if we use a loop that encloses a topological charge, we'll have that the result of this calculation will be a number that is directly correlated with this value Q I showed you before. In particular, this definition also tells us that we can define a net topological charge for a system that has to be consistent on how the parameter is oriented in the boundary of our system. In that way, if the boundaries of our system don't change, it means that the net topological charge must be conserved. So as a consequence, in that cases, in continuous transformations, we can only create or destroy topological charge in pairs. So now that I defined these key concepts, I want to apply them to explain a little bit further in how we can find these topological defects in the nematic fluid crystals. So usually, in order to observe topological defects in a nematic fluid crystal cell, we use what is called the polarized optical polarized dynamic microscopy. What we do is that we put two crossed linear polarizers between in the two sides of the nanomaterial crystal cell, and we pass a white light source through this whole system. The idea is that through the camera we can see how the system is affecting the light in different points of this cell. We also use a voltage difference that is sinusoidal, but it has a very large frequency in order to have a Kapitz effect that allows us to take this voltage as constant as in the theory and the experiments, but also allow us to inject and dissipate energy constantly in the system in order to have this self-organization. So in the video, you can see that if we pass the Frederick voltage, we will have the emergence of topological defects. In particular, we can observe topological defects with mass plus and minus 1/2 topological charge, but they are very, very unstable, and they annihilate each other or destabilize in topological defects with plus or minus 1 topological charge. The idea is that if we take the vector director, we can make redefinitions in order to define a complex ordered parameter that accounts for the dynamics of our system. And this complex parameter can present some topological defects that will be consistent with the physics that is occurring in the nanomaterial crystal cell. In particular, first of all, if we use this ordered parameter, we can couple the equation for each one of these components of the vector director in order to have one complex equation for the whole system. And this is called the Ginzburg equation, which appear in other contexts because this will be robust phenomenon. In this case, in particular case, we will have the mu is the bifurcation parameter. It has to be with if we are above or below the Frederick transition. Delta will be an elastic anisotropy, which will tell us if the order parameter will be more twisted or splayed around the different singularities. And we have this Bertin-jet derivative that allows us to write this equation a little more consistent. So the idea is that in this setup, we will observe the nanomaterial crystal cell will work as a wave plate, which non-uniformly change the phase of the light in different points of the system. And this intensity in different points of this cell, different points of the plane parallel to the nanomaterial crystal cell, will give us information about how the molecules are oriented in different points. As the final intensity is proportional to this sine plus the cosine of the orientation of the molecules, we can use a field in simulation that is called the polarization field, which is the real part plus the imaginary part, that will tell us sort of the same information that we are watching in the experiments. So this is a simulation that shows something very similar to what we do in the experiments. So now that we have this complex parameter, we can use an ansatz with topological defects to understand which kind of topological defects we can find in these kind of systems. If we use the Ginzburg equation, the advantage that we have with this equation is that we can define a sort of energy that we call the Leibniz functional, and in function of the behavior of this functional, we can see which kind of solution are stable or more stable than others. In particular, if we use an ansatz using arbitrary topological charge, we can, and after straightforward calculations using the condition in the Leibniz functional, we can find that the only topological defects that are locally stable in the system are the ones with +1 topological charge that we call vortices and -1 topological charge that we call antivortices. By the other hand, it's important to understand that the way in which the order parameter is oriented around the singularities will tell us or will be correlated with the elastic anisotropy of the system, if it's more twisted or more splayed, depending in the relation between K1 and K2. Okay, so now that we now understand that we have this topological charge, these topological defects in the nanomaterial crystal cell, we start to understand which kind of effects we have if we induce a topological forcing in this kind of system. Because until this point, we were only using an electric field that was perpendicular to the plate, but we can also have an electric field or a magnetic field which have a component that is parallel to the plate. In that cases, these extra terms will give us information about how the geometry of these fields, this external field, impose some boundary conditions or some conditions in the system. And in particular, for example, if we use a magnetic ring, which these approximated magnetic fields, we will have that the structure of the magnetic fields will tend to align the molecules in a way that gives us a boundary condition and that induce a defect in the center of this, or roughly in the center of this magnetic ring. In this case, also, we have the advantage that the magnetic field of this structure has an axial symmetry, which means that the phase that we will have in this magnetic field will be or can be modulated with the azimuthal coordinate. Also, we will have that the mu parameter, in this case, will be separated by a factor mu sub 0 that will tell us if we are below or above the Fourier transition, and a factor mu1 that will tell us how in different points of the cell, the magnetic field is reorienting the molecules in the system. So the idea is that if we use this magnetic field, for example, we can and in order to observe clearly the effects of this topological forcing, the magnet, we use space of parameter in which nonlinear terms and diffusion effects can be ignored in the system. And so we will have an ansatz which have at least one vortex in the interior of this inner edge of the magnetic ring. This is called a Rayleigh vortex that can be achieved by this magnet, or it can be achieved by electric fields that have this kind of geometrical configuration. And it's called a Rayleigh vortex because the profile of the intensity of the light that passes through the cell roughly follows the Rayleigh distribution. It's not another thing in the name, sorry. So this first observation tells us that we have a vortex trap in the center. And so now we want to study which other kind of topological structure with this +1 topological charge imposed by the boundary conditions we can have in this kind of system. So if now we are above the Fourier transition, more complex configuration with this +1 net topological charge can be observed. In particular, we can observe this vortex spread, which is a consequence of how the molecules are oriented by the geometry of the magnetic field. In particular, we will have that in the center, we are inducing this vortex that is roughly in the center, but we will see that it's moving. And the orientation of the molecules near the inner edge of this magnetic ring will generate a line that will destabilize in different defects that then will annihilate in pairs of different topological charge until we obtain only two vortexes of opposite topological charge in opposite sides of this circumference. The idea is that this structure has a net topological charge equal to +1. We have this is a -1, this is a +1, so it's 0, and we have this +1 vortex in the center. But the particularity is that we have traveled these vortices that before were annihilated in order of minutes. So now we can study the dynamics of the vortex of the center, for example, of the negative charge in the edge of this system. Also, we observe in simulations that for other kind of magnets that are not axially symmetric but have a phase jump of 2 pi in their magnetic field, we can find also a single vortex in the center, and we can also find this kind of structure in some point of the cell, imposed by the boundary conditions, imposed by the geometry of the magnetic field. Okay, and now that we have this evidence of the trapped vortex by the topological forcing in the system, we can start to indicate what kind of system or what kind of transitions we can have for this trapped vortex. In particular, first of all, I want to talk about the voltage-induced vortex triplet instability in this system. Experimental observations, preliminary experimental observations suggested that the triplet was an unstable state of the system for values above the Frederick transition. However, for a large enough intensity of the voltage, the central positive vortex annihilates with the negative vortex of the triplet. And so, after some minutes, in this case, the video is speeded up. After some kind of like half an hour, these two vortex will start to come together to each other, and then will annihilate because they have opposite topological charge. The interesting stuff is that we are left with a system that has a plus topological charge, but that now is pushed to the boundary of the system. It's not in the center. So here, for example, we can see the different behavior of these two cases, and we can clearly see that these two systems, for low voltage and large voltage, have a different behavior, and then we have a transition between these two kind of systems. And we want to study the transition for a critical value of the voltage, which is above the Frederick's transition. So we start to change the voltage, and what we discover is that the separation distance between the vortex in the center and the negative vortex in the edge start to decrease when we increase the voltage. So then we have a critical voltage for which the separation distance becomes 0, and obviously the two vortexes of opposite topological charge will annihilate. However, we also have a second critical value for the voltage. If we start to decrease the voltage, we will encounter another value for the voltage in which the vortex triplet appears again. These two vortex appears from nothing, and then we recover the triplet structure. So we have a transition that has hysteresis, and we want to understand if the topological force of Gibbs-Landau equation has this kind of transition, and so accounts to the experimental observation that we are having here. So we start from the topological force Gibbs-Landau equation. In this case, we use delta equals 0 just for simplicity, but without losing generality. And the idea is that if we start to change the parameter mu sub 0, which will tell us, which will be related but not directly equal to the voltage that we are applying in the cell, we will have that if we start to change mu, we obtain the same behavior. We obtain that for some values of mu above the Frederick transition, but below some critical value, we'll have that the separation distance start to decrease, but stay in an equilibrium at some point. But if we start to increase mu sub 0, there is a point in which these two vortexes start to get together and then annihilate to each other. If we make the Virchow diagram for this transition, we obtain this roughly the same results as in the experiments. So we understand that this equation has this transition, accounts for this transition that we observe experimentally. So now that we understand that this equation has the transition, we want to understand if we can have an equation for the dynamical behavior of this separation distance between these two vortexes. So we use the topological force Gibbs-Landau equation, but in the using as perturbations the effects of the magnetic ring in the equation. We also use as approximation that the two vortexes in the edge are far enough to not affect directly the amplitude of the amplitude of the parameter of the vortex in the center, and then we can build ansatz for this order parameter to understand if the separation distance of this vortex has the same transition. So after straightforward calculations, we can achieve a dynamical equation for this system, which have three terms related with these three functions. The function gamma 1 has only effects of the magnetic field, and is related with the red curve in this plot. The idea is that this will, as if negative, it will tell that the distance will start to decrease until some point in which this value is very roughly similar to zero. And then other kind of interaction will be more important in that point. This will tell us that the central part is roughly unstable and will be more stable if we start to increase mu sub zero. Gamma 2 is a combination of the effects of the vortex in the edge and the magnetic field. It doesn't have too much interpretation here. And the last term, gamma 3, that is the blue curve here, is only directly related with the interaction with the vortex in the outer ring. Something important to understand is that this last term, gamma 3, is always negative, which means that the two vortexes will want to annihilate each other if the magnetic field were not present. So now that we have this dynamical equation, we try to understand if we have the same kind of transition, and we find a region of parameters in which this transition is observed. We have the hysteresis, and we can also can account for the points in which we have the unstable state. So as a conclusion for this part, we can understand that under strong magnetic fields or other fields like an electric field that have some geometrical features, we can trap vortex, we can induce a net topological charge in the system, and we can trap vortex in different parts of the system. Also, the position and number of vortices in this kind of topological structures can be done by varying the voltage, for example, or other kind of parameters. I suspect that, for example, temperature will also change this behavior. And based on an amplitude equation, that is the topological forcing Landau equation, we recover sort of the same transition. As future to work for this part, we will have to test with other kind of configurations with other magnets, for example, the parallelepiped magnet. And we can try to find a model which accounts also for the coupling between the phases of the different vortices that probably will tell us about how the vortex also moved in the other direction, because here I was only telling that it was moving in a straight line. And so finally, I will want to pass to the other original results of my PhD research that are related with the low frequency voltage effects in this nematic Lie crystal cell. So as I told you before, usually these kind of experiments with nematic Lie crystals are with voltage that are with a frequency in the order of the kilohertz in order to have this Kabitz effect that allows to model it as a constant voltage, but also we can have the dissipation and injection energy that we need in nonlinear systems. But in the cases in which we use very much lower frequencies, for example, in the order of hertz, we will find some kind of states that are not of equilibrium, but they are of an oscillatory kind. For example, the first that we observe is the dancing vortex, which we call in the case in which the nucleus or the molecules around the phase singularity are changing their direction, and then it's like the vortex is rotating around the space singularity. It's important to understand that the rotation is the result of a persistent perturbation in the molecules because they are changing their orientation in order to achieve different orientations. We observed that also the core of the vortex, the phase singularity, is like breathing. So we account for the changes in the amplitude of the rotation and the amplitude of the breathing of the phase singularity. We want to characterize these experimental observations to understand which kind of frequency we are observing in this movement, etc. So first of all, the results suggest that the system has an harmonic response in the frequency in which the vortex is oscillating and breathing. We have more frequencies, but the main frequency is the same frequency that we are using in the external voltage. We also studied how the maximum amplitude of these two oscillatory features of the system are changing when we change the frequency, and we obtained that the amplitude of the breathing and the reorientation of the arms is proportional to the inverse of the frequency that we are using in our external field. So we want to achieve a theoretical description for this system also, or at least we want to see if we can recover this in simulations. But unfortunately, capacitive effects in the nematic Lie crystal cell that we will have in this region of parameters for the frequency are difficult to address theoretically. So in order to advance, go forward in this part of the research, we use a phenomenological model based on the experimental observation that we have. So we started with the topological first Gibbs-Form lambda equation, but we promote some of these parameters in order to have, first of all, a sinusoidal behavior that is justified by experimental observations. For example, the light that we can see in the system is oscillating, and that's a direct consequence of the bifurcation parameter. And also, the rotation of the arms is a consequence of different orientations of the molecules that is accounted in the delta parameter. We also use this complex parameter K in order to couple to have a coupling between the phase and the magnitude of this ordered parameter. As we can see, the rotation is very more intense in the center near the phase singularity that is far away. So we will have coupling between the phase gradients and the amplitude of this ordered parameter. If we do simulations of this phenomenological model, we can see, at least in the part of the rotating arms, that we have the same results. We have an oscillatory state, and we have that this oscillatory state has a response that is harmonic, that is with the same frequency that we use in these parameters. So as the simulation shows that we have these dancing vortices, we want to understand if we can recover the behavior that we observe experimentally, at least using perturbations in this equation. So we use an ansatz considering perturbations in both the magnitude and the phase of this ordered parameter. And we use the new parameters in the phenomenological model as perturbations of the original Ginsburg lambda equation without topological force. If we consider this and we use a perturbation, if we use the perturbation here, we can understand how these perturbations evolve in time. So we obtain that both the breathing and the rotation of the arms have a sinusoidal behavior, as we can see in the Fourier analysis, and also have the Bohr law inverse to the frequency that we observe experimentally. Okay, and we could not research too much in the dancing vortex because I was trying to play with the frequencies. And we thought, what happens if now we use a frequency that is very, very low in order to obtain large rotations, at least in the arms of the vortex. And what we obtain is what is called a vortex lattice, the creation or the appearance of that vortex lattice. So as I told you before, the amplitude of the rotation of the arms is inversely proportional to the frequency. So very low frequencies will tend to rotate very, very large the vortex. So there will be a point in which the neutrons of the vortex will collide with each other that, physically speaking, tell us that there is a moment in which the elastic stress from this rotation is very, very large, and then the system prefers to create a pair of vortices instead of continuing the rotation. This process starts to occurring again and again with the different vortices that we are creating, and there is a point in which the number of vortices in this lattice will remain constant in the same points of the different periods of the external field. As this is an oscillatory kind of state, we will not achieve an equilibrium, but we will have that in the same point of each period of this external voltage. In some point, we will have the same number of vortices, and the lattice will not start to grow indefinitely. So we wanted to understand how we pass from this dancing vortex to this vortex lattice. So we studied the transition, and we discovered that there is a critical value of the frequency in which the number of vortices start to grow, and lattice will have more and more vortices if we have a low frequency. Also, as the vortices are created in pairs of opposite topological charge, the net topological charge of the system is not changed, and there is no break symmetry. So we have here a topological phase transition, like the one in the cavity model that we have in quantum mechanics. So we wanted to understand if the phenomenological model that we use in the dancing vortices has these same features that we are observing here for low frequencies. Unfortunately, as we will have more capacitive effects for lower frequencies, we will not. We will have to use this phenomenological model. And what happened is that if we only use this part of the equation, we'll have lattices, but these lattices will disappear and we will obtain again just one vortex. But in some moment, after a lot of thinking and to understand which we will add to the phenomenological model to achieve the vortex lattices, we add an inertia term, and this inertia term allows us to have persistent persistent vortex lattices. Now, this inertia term is inspiring the fact that when we are in low frequencies, we are exciting the molecules in the same time window that the molecules have to relax. So we are constantly moving the molecules, and we can and we suspected that we can add the inertia of this moment in the system to see if we have this persistent topological vortex lattice. Sorry. In the phenomenological model with inertia, we have the same transition, or at least a transition very similar to the one that we observed experimentally. But at least we could not convince that this inertia term was the response to the system. So I didn't go further in the theoretical explanations. Also, there are other kind of systems in which this kind of lattices are observed. For example, similar cases, there are similar cases, sorry, where vortex lattices are induced by thermal gradients in a nematic fluid crystal set, like the ones I'm showing here. And these vortex lattices are induced by convection rolls that are induced by this thermal gradient. In our case, for low frequencies, one of the of the capacitive effects that we have is electroconvection, and this electroconvection can also generate this kind of convection rolls in our system. So it is it could be that the origin of these lattices is from these convection rolls, as we can observe, for example, in the case of the magnetic ring, in which these convection rolls are distributed with a roughly azimuthal symmetry. And in the case of a parallel ribbon magnet, we have a vortex lattice that is very, very similar to the one that is obtained by thermal gradients. So this suggests that maybe the convection rolls that are from the electroconvection are the main mechanisms that can be generating these lattices. So as a consequence, as a conclusion, low frequency voltage induce capacitive effects in the system and then induce non-equilibrium oscillatory states in the nematic fluid crystal set. The complexity, we cannot obtain theoretical models, at least not in the objectives of this thesis, but we could have phenomenological models that capture the principal features of this phenomena that we observe experimentally. So as future work, we can find a theoretical model from first principles using Leslie Erickson theory to couple the dynamic of the fluid with the capacitive effects that are happening for low frequencies in the voltage. Also, we can explore the observed phenomena with other kind of nematic fluid crystalline materials in order to, for example, in order to optimize, different experimental features that we observe. So, for example, the amplitude of the velocity of the rotation of the vortices, or the velocity of the formation of these vortex lattices in the case of very, very low frequencies. So that was my presentation. I want to say thanks to Anit and Miro for the financial support of this research, the Facultad of de Ciencias Físicas y Matemáticas for my academic formation, and the Laboratorio de Fenómenos Robustos en Óptica, LAFER, for all the sharing moments and all the different commentaries I have through this presentation. Thank you very much.
Thank you, Roberto, for being on time. So I invite now the members of the committee to ask their questions. I guess we can start with Dr. Massimo Vidici, if it is okay.
Yes, okay. Can you hear me?
Yes.
Yes.
Okay, great. So I don't know if it is like in France, but I think that the first thing that I would like to say is that I want to congratulate with Roberto for this thesis. I discussed already the manuscript details with him in the first meeting, and I found it very interesting, very well written, and the amount of work that has been produced is impressive, both experimentally and both theoretically. So I would like, before asking any question, to congratulate Roberto for his work. Okay, then I have a few questions. Maybe the first one is, so you said that you use white light to reveal the structure of the matter of your liquid crystal. And I was wondering, I mean, the effect on polarization going to depends on the wavelength. So the effect of using white light, well, is it really white light, or is it just a LED light centered in the visible range? And if it's really white light, what would be the advantage and the difference of using, for example, monochromatic source? I mean, what is the impact that you would expect when you are showing your interferogram?
Okay, I guess I think I understand the question. I want to just put some. This will work. So we use a white light source. We use a. I don't remember the technical details, but it's not a LED. It's a bulb. It's a light bulb. And the idea of using white light source instead of monochromatic light is because the material interacts with the frequencies in different ways. For example, because of their birefringence nature of the material. So, for example, this liquid crystalline material in particular blocks almost all the blue light. So, for example, if we use a blue light, it will be probably dark, or we will not have the optimal light to observe the experimental features that are observing. And then, if we use monochromatic light, it will probably change in the intensity that the phenomena that we are observing. I remember that this material in particular allowed to pass almost all the red light. So, for example, I could use only red light, and the results that I'm watching in the experiment will be probably the same or very similar. The same with green light, that is a little more fainted, but is also observed. But that will be the difference.
And what you show there, I mean, this color scale, its intensity is proportional to the light intensity, right?
Yes. I mean, if I do you mean if I change the intensity in the white light source, the intensity on the?
No, I mean, what you are plotting here in a color scale is the intensity that reach your camera, your CCD camera.
Exactly.
Okay.
So you can
nothing
see
to
that
do.
it's mostly,
Okay.
it's mostly red and yellowish.
Then I have a question about the modal decomposition, because this is something that so you say that you may have different modes because you impose the boundaries. The boundaries with the anchoring effect and so on. But at the end, I mean, do you think that you are always working with the same mode, or you may have some jumping between different modes? And if you have jumping between different modes, what will be the impact of the light which is transmitted?
Yes, I didn't add it here now that I remember, but the idea is that if we start to increase the intensity of the voltage, we will achieve other kind or I suspect that we will achieve other modes in this vertical direction. And I don't have the plot here, but there is a experimental result that if we start to plot the intensity of the light that we see in the camera, there is a point for the voltage in which this intensity starts to decrease and then start to increase again. And it happens several times. So I suspect that every time that this happens is a point in which we are achieving other modes in the vertical direction.
So for the voltage that you have, you are with M, which is equal to 1. You are in
Excuse
the you are in the fundamental mode in some sense with the
yes.
voltage.
Yes, that's because we are above the Frederick transition, but we are very near the Frederick transition.
Okay. Okay. So you have basically just half period in terms of the vertical structure. Okay.
Yeah.
Okay. Okay. Another question. So when you put a magnet, your boundary conditions are going to change. And so this, I was wondering, okay, if I understood correctly, you insert the effect of the magnet as a perturbative term. But I mean, this, I mean, how I don't see the relationship with the anchoring boundary condition driven condition. See, so you have anchoring, and then you have the magnet.
Yes.
So, I mean, how do you conceal these two effects? How can you?
Yes, the effect of the magnetic ring, even if I draw it as if the molecules were directly oriented with the magnet, in fact, is giving a preferable direction to fall when we achieve when we are above the Frederick voltage. It's like we don't have now that all the angles are the equally the same probabilistically speaking, but we have a preference for one considering direction in each point of the cell. So when we are above the Frederick transition, then we will most probably fall in that direction. As we have millions and millions of molecules, this will happen in the system. Now, with the anchoring, we have that the anchoring will not have a problem because it's mechanically speaking, is stronger than the effect of the magnetic ring. So the magnetic ring will only affect in the more inside of the material of the cell. Yeah.
Okay. Okay. So I don't know if I have time to ask more questions, or should I? I don't know if we are time limited.
No, if you have more questions and you want to ask them now, you can, or maybe you can wait after a first round of questions, as you wish.
Yeah. Okay. Then I will stop here. I don't want to steal too much time. So
Okay.
yeah. Okay. Thanks.
Yeah,
Thank
thank
you.
you. So perhaps we can continue with Sylvain Barbaille.
Yes, thank you. So, yeah, first of all, I would like to congratulate Roberto for his very nice and clear presentation. Also, it was a great pleasure to read the manuscript. It's always very clear and detailed. So, we already had the opportunity to discuss some technical aspects of the work last time. Nevertheless, I have a few questions. And my first question would be, let's say, a kind of follow-up question of the one of Massimo, who asked a question about the white light source. And I had the same question in my mind. In fact, during your presentation, I wondered to myself, but why doesn't he use a laser light, or let's say... And so I have two questions. First of all, do you have what is, according to you, what would be, according to you, the interest or disadvantage of using a source of light with, let's say, longer temporal coherence? And it's not clear to me at the moment, in your measurements, you use black and white camera or color camera?
I use color camera for some observations and black and white for
Okay.
others.
So it's very
Yeah.
interesting because when you have, I suspect that nevertheless you have some interference effect in your system which produce this color, more or less, that you have otherwise. And so my question is, do you think it would be possible to extract some more information using the information of the color from your color images?
Yeah, in fact, as in particular in the case that we have the vortex in the center, or the vortex triplet, as we have this kind of sort of conical structure for the light, we will have that the concentration of colors will change in radially speaking. So we can have information about how the molecules are oriented with that intensity, as I understand, because as I suspect. Sorry. So first of all, we can have information about the more precisely orientation of the molecules around the phase singularity from the different color channels, if I can say that.
But the alignment, let's say, of the molecule give you the intensities, and you have the difference with the different wavelengths. So what kind of information do you think you could extract from this? Is it useful or not?
From my point of view, or for the things that I was observing, it wasn't important.
For instance, you could try to filter out some light after the observation. To say you take a camera and then your image, you filter out certain wavelengths to see if you have the same kind of image. Did you try that, or would it be interesting to try that, you think?
I tried it very early in the research, but I dropped it because I didn't have too much information from that, at least in
Okay.
the things that I was researching in that moment. But yeah, for example, the different colors, as I told you, can account for the different angles, but not in the plane of the cell, but in the direction that is perpendicular to the plane. In particular, I don't know if I have no, it's too fast. But as this triplet is generating, for example, we have like fronts of colors from the center to the edges that I suspect that is a consequence of this transition happening. I can have information from that colors that will tell me how this angle is changing in time, because it's correlated with the color I will be seeing, as I understand, optically speaking. But yeah, I think that's the kind of information I could have, but it wasn't too useful. I think that I was researching.
Do you think okay, so you could have some important width, let's say height gradient of your cell. Let's say, how do you make sure that your two glass are very parallel one to another? You have some spacers in material, or how do you make sure that
Yeah, they are manufactured by external laboratories, and they assure us that the difference in the width is constant and is the one that
so
is.
they are parallel to a very good precision?
Yeah.
Okay. So
Yeah, experimentally speaking, we can also say that, because if there wasn't some angle, we should have other kind of phenomena. Some, for example, labyrinthine patterns or something like that. Or we should have some kind of dynamics to the parts of the cell that is different that way.
So I have another question concerning the arrays of vortices. So I would suspect that from practical point of view, it's kind of interesting to be able to have arrays and to be able to control the arrays of vortices. And so I would like to know what is your opinion about what would be the best way, according to you, to control. If I have an array of vortices and I want to control individually the vortices, what would be the best technical solution, you would say? Is to try to control the magnetic field below these vortices, or how would you, what would be the best according to you?
Yes, I imagine that the best way would be to make a precise magnetic field, or different magnetic fields in the region of the cell, with which we can, for example, create different +1 topological charge, or different triplets in different points of the cell. The only disadvantage is that the dynamic is very slow in this region for the frequency. For example, if I have the magnet and I displace it, the whole structure will not displace with the magnet at the same time. We'll have some kind of relaxation time to recover the triplet in the new new position.
So everything will be super slow. So you have to wait a
Yes,
super
yeah.
long
So
time to.
that's why I suggested that for future works we will explore with different crystalline materials that speed up that feature. Yeah.
Okay, and so my last question of this round would be, so at some point you said that based on theoretical arguments, that the only stable vortices that you can have is with topological charge +1 and -1, and this is based on the assumption that you have this functional, Lyapunov functional. And so okay, obviously you have a model, so it models reality. So how strong you think this result is? Do you think you can, in certain circumstances, stabilize other type of vortices? Or what would be the physical parameters that would break this Lyapunov functional that makes you that the only stable vortices are +1 and -1?
Yeah, in fact, the +1 and -1 are not the final stable configuration, so to speak, but the stable configuration for this kind of system, only using the Gibbs-Lambda equation, will be a homogeneous state. These vortices will start to collide between opposite topological charge or with the boundaries. So if we wait like 10 minutes for this,
But if you have only one, if you are in a triplet state, you have only one, it doesn't move.
No, yeah.
Okay, you mean this situation doesn't apply to this triplet state? Yes, it applies.
Yes, but we should add some terms in this Lyapunov functional. We could find the
And in that case,
because we have a different PD. We have a different equation for that.
Yeah. Okay, and it breaks everything. Okay. Okay, so thank you very much. I will stop for my question for now, and congratulations again.
Okay. Thank you. So we continue with Stephen, if he's there, because then we are getting closer to our faculty.
Yep. Hello. Thank you, Roberto, for the presentation. It was very good, as was the presentation last week. As is your thesis document. So I wanted to begin by congratulating you to join my colleagues in congratulating you. Yeah, so I asked several questions last week. I guess I just had one question, and it was related to this last question of Sylvan's. So in optics, I mean, I come from the field of optics, so you can have, say, vortex beams where, such as, different like Laguerre-Gaussian modes or Bessel modes and so on, where there's really no limit to the topological charge that you can have in the wavefront. And so I was wondering, what's the physical difference between your system and the optical system that does not allow you to have these, high order topological charge?
I will say that is the elastic stresses in the material that don't allow us to have the orientation in the ordered parameter to have this kind of other topological charges. For example, if we have the +1 or the -1, but the +1/2, -1/2, I imagine that there will be a difference between the displayed parts. One part is more, so to speak, how can I say? It's more shrinked than the other ones. So I think the elastic stresses are physically speaking, the limitations to have these other kind of topological charges in this system.
So the fact that, I mean, all of the molecules are say, interacting in several different ways, probably, as opposed to photons in a beam of light, really don't see each other, right?
Yeah,
That's the simple explanation. Okay. Yeah, great. So that was my only question. Again, congratulations, and thank you again for the invitation. It was a pleasure to see your work.
Thank you, Steve.
Okay, so we continue with questions of Michal.
Mike.
Yes. So thank you very much for your presentation. It was very good, and And it's an impressive thesis because it has the experimental part and the theoretical part, mathematical model. So that's very nice combination. And because I'm a mathematician, so I will ask you about the mathematical part. So let's go to this dancing, for instance, the dancing vortex. So let me just confirm first that the response of the system is the frequency of the response of the system is exactly the same as the frequency of the forcing, right?
Yes. Yes.
So
For example, in this case,
normally,
sorry, continue.
so normally you can think of it as follows. You take, for instance, you can take a harmonic oscillator, damped harmonic oscillator, and force it periodically, and then you will find a periodic solution to this problem
Mhm.
with exactly the same period. It's different when you periodically start playing with the coefficients. And in your system, what I don't understand is why you play periodically with your system with the diffusion coefficients, but not with the forcing, while it is the forcing which is periodic, in my opinion.
Yes, but the first thing that we're speaking here is from the electric field, and the features of the electric fields are contained in the bifurcation parameter, for example. So in that way, the mu will have a sinusoidal behavior because the electric field have a sinusoidal behavior.
This is correct, but what about the other terms?
No,
For
the other
instance,
terms are only from a phenomenological point of view, because, for example, the delta, the elastic anisotropy, I mentioned it before, that is directly related with how the molecules are oriented around the phase singularity. So if this orientation is changing, is because the elastic stress in the system is changing, and then I promote the elastic anisotropy as an oscillatory term too. That's my only argument from the phenomenological point of view.
yes, but you also have some kind of forcing, like from the magnetic field you have forcing, but from the electric field you should also have forcing, right? In the problem, or no?
Yes, but from the magnetic field, it will be stationary. It will be constant because the magnetic
Yes,
field is.
but from the electric field, no.
Yeah, and that's what is affecting the mu parameter, for example, directly. Because
But
mu. Let me go back maybe to the definition.
okay, so let me change the question maybe a little bit.
Okay.
So what if you try to make your model as simple as possible, as minimal as possible, and let's say you only modulate mu in time, but not k and not delta, not
No.
headers.
Yeah, in that cases, I don't have the dancing vortex. I only have the breathing in that case. In fact, that the core of the phase singularity change and are all around because the bifurcation parameter is related with the intensity of the light that we see in the experiments. So if I only use mu, we don't have the dancing vortex. Yes.
Okay.
Yes, we will have this breathing characteristic of the phase singularity, but the dancing part will not be achieved.
Yes, but
Sure.
when you see when in your I agree with that. Okay, I understand this. But in the very equation that you have here, you have two terms, two forcing terms. One is with B, which is, I suppose, from the magnetic field part, right? And the other one is from the electric field part. And you don't seem to include this part in your model, phenomenological model. This is my question. Why not?
Yes, I mean, I add that part. I put a mu sub zero that is constant, and the mu one that is oscillating is because the voltage is oscillating because electric field is oscillating.
Yes, exactly. So where is this term in your phenomenological model?
Is the sinusoidal term that I add with the mu1, but I don't have it directly correlated with I don't have it written as function of the electric field. That's the only thing. But
Okay.
I am imposing that this mu1 part is oscillating.
Okay.
Yeah.
Okay. Well, thank you. So this I guess it's my question.
Thank you, Mike.
Okay, thank you. Marcel, you continue now.
Okay, thank you, Felipe. Okay, so first of all, I'd like to also to congratulate to Robert. For me, to be honest, it's a very nice work with Robert from the scientific point of view, also for the human point of view. Robert is a very nice person to work, so I'm very happy for that. And the quality of the scientific, as the other member of the committee remarked, the work of Robert is very good for the theoretical and also for the experimental point of view. So I'd like to congratulate for that, Robert. Even the document was very well written. So thank you for that. Okay, so I have also a small question for you. So my first question is related to the null climb because it's a very maybe sometimes difficult to explain because are not physically, it's your choice. But my question is, which is the role of this kind of null climb? Why they are important and why do you consider that relevant?
Okay, so from the physical point of view, first of all, the null clines are the part of the cell in which the molecules are aligned with one of the two polarizers that I show in the experimental setup. But as you said, it is not an experimental feature per se, because if we change the orientation of the polarizers, the orientation of the nucleus will change. But the important part of the nucleins is that they allow us to find these topological defects. Because, for example, if we didn't use the crossed polarizer, the topological defects will only be like a point. And for example, we could not tell from the negative and the positive topological charges. We could use other kind of polarizers, for example, circular, quarter wave plates, but not crossed, but in 45 angle. If we use that, we will also have more information about these defects, but we will have, like, for example, the shape of the defects, and then we can tell what is the positive and the negative one. So I could tell that the importance of the null clines is, first of all, where I can encounter vortices, where I can encounter topological defects, and which kind of topological defects I have, if positive or negative.
Okay. Okay. So they're useful for recognized vortices. This is the point, more or less.
Yes. Mhm.
I have another physical question related to the inertia, because also this is very, there is a lot of discussion about the role of this term, because okay, for us it's okay for the explain our phenomena, but the question is, which is the physical origin of this term? It's a little controversial.
Yes. So as I told before, we add this inertia term in a series of attempts to recover the experimental observations in the model, and this worked. From the theoretical point of view, I never had the connection between the first principle and this term. I think that, as I say in the next slide, it could have to be with these convection rolls. Maybe the dynamic that these convection rolls are inducing has to have this inertia term. So maybe from first principle, this inertia term can appear, and this effective moment of inertia maybe has to be with or is related with this electroconvection, and this will be related with capacitive effects in the magnetic crystal cell. So then I think that physically speaking, we could have the inertia term. We could have it from this dynamic, but it's not something that I will research too deeply in this PhD. Yeah. But
Okay,
from the lectures, from the reading I did, I think that it can be connected with the convection rolls and the dynamic that is inducing.
Okay, so my last question is, okay, this time is possible maybe imagine the possibility to observe wave. What do you think about that?
Yes, I mean, if we have inertia, we can have wave solutions. In fact, maybe it's connected with the electroconvection patterns that we see as waves in the system. I don't have an image here or a video here, but we have this electroconvection movement that is literally manifested as waves in the system. And maybe this electroconvection is also related with this inertia term. If we have these waves in the system, that even in some point I saw that it was appearing and disappearing for large times, it could also be an evidence that we have inertia effects in this region of parameters for the frequency.
Okay, thank you, Roberto. Thank you, Felipe.
Thank you, Marcel.
Gracias, Marcel. Entonces le pregunto al público si es que tiene alguna pregunta para Roberto. ¿No? Ya, no hay preguntas del público. ¿Alguna pregunta más que quiera hacer algún miembro de la comisión?
In English, Felipe, don't forget.
I'm sorry. Yeah, for the committee, I'm asking if there is any extra question you would like to ask to Roberto.
If I can ask one more question, the series that I had before, if you wish. So
Yeah.
I would like, so at the beginning of the presentation, you will illustrate different elastic forces, the different contribution to the elastic energy, right? So what I wanted to know is how do you evaluate this weight? So K1, K2, K3. So is it a experimental characterization or something that comes with the data of the cell of your cells or your liquid crystal?
I mean, I think both. First of all, when we work with some material, we can have information from these different elastic constants. From my experimental experience, the only one that I could measure will be K3 because it's related with the Frederick transition. So I can see in which value of the Frederick voltage, what is the value of the Frederick voltage, and then use other parameters to obtain K3 for my material and other materials that have this Frederick transition. K1 and K2, I don't know how to experimentally measure them, sorry. But yeah, they are information from the material that we acquire in the laboratories, the external laboratories. Yeah.
Okay, well, that's it. I don't have further questions.
Okay.
Thank you, Massimo.
Thank you very much. Marcel, tú tienes el control de Zoom. No sé cómo prefieres hacerlo para la deliberación. Si sacas a Roberto o le pido a todo el mundo que salga de acá.
Voy a sacar a Roberto y después lo llamo y que entre cuando terminemos, pero tú tienes que estar, Felipe, porque eres un testigo de fe o quieres que discutamos sin ti. Podemos hacerlo.
Claro, pero eso, a ver, tendrías que... con el teléfono me puedo conectar, ¿o no?
Puedes conectarte ahí mismo.
Ustedes salen. Ya, bueno, entonces
Ok, voy a cortar.